All right, let's go over Ask and Bitwise. This assignment was designed to teach you to appreciate the standard library a little bit. Here's all stuff that is trivial to do. If you have a standard library in assembly, kind of pain in the ass, right? Kind of a pain in the ass because you got to do everything manually. There is no, right? No reference to GCC, no reference to G++. It does not link the standard library in. This is going to result in a executable that is quite small, 1.8K, which is far smaller than you would get even with like Hello World. I think Hello World, it's like 5K or 6K, right? So if you're going to be doing development on like an Arduino or something like that, that can have very, very limited RAM. The difference between 1.8K and 6K of RAM is like, on a system that has 8K of RAM, that's a pretty big difference. And so, in the embedded world, knowing assembly is pretty essential. They're even doing assembly. Oh, sorry, they're even doing embedded programming with C++ these days, which is some kind of cool stuff. But if you're going to be working and programming microwaves and remote controls and LCD projectors and stuff like that, anything where cost has to be kept to the absolute minimum, then knowing assembly is pretty important, I would say, even today. I ran the program for you guys, like how to run it. You type in how many letters, 3, and hello, and it reads in 3 letters, and it reads a letter in one at a time, and does this, and it reads through the array one at a time. It's not getting inputted one on each line. So if you guys want to fix that, go for that. I can regrade it because I know a lot of you guys got a lot of work done on it, and also I will allow partial credit on it. So if you guys got like halfway through it, then just message me and I'll give you partial credit on it, because looking at the grades right now, it's a bloodbath. So so this is how you, by the way, build a program. Like if you're going to do it manually using the assembler. So use ask to go from a .s file to a .o file, or the call thing, and then you call the linker, and that links the program together like that. And do we really need to read the full string read thing instead of one char at a time? I could just show you how the thing runs, like 5, and then I type in hello there, whatever, it doesn't matter. It reads in 5 characters, right? It loops, however you want to put it. It reads 5 characters, uppercases them, and then does the diamond pattern, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So I'm not going to show you the whole thing because I'm going to allow you guys a second crack on it, I guess. But this is how you start a program if you are not using the standard library. If you're not using the standard library, it's not main. It's not main. Start. Start is the actual beginning part of a program, not main. Main is just a C++ thing. Okay. So, so this code here loads from the data segment the address of the string greeting. Yep, and then it puts that into register 1. Register 2 has the size of the string, and again there's that trick that you can use with the difference of the 2 labels to do that as a bit of a nicer way of doing it. That puts the number of characters to output. This chooses the write system call, and that invokes write, and so that will print welcome, whatever. And then to read a character, so let's see, I'm going to be reading from standard input, 0 is standard input, right? I load the memory address of the string, and make sure you have enough room for that. Like, so what I did was I just made an ASCII that, down here, you can see I just made an ASCII that was big enough to hold any string that could possibly be typed in. This is horrible, by the way, but but because the write system call tells you how many bytes to read, it won't overflow. So I just made a giant string that I could write into, And then I have a giant array of dots, and so when I do the outputting, I just print from the dots over and over again. Yeah, so let's get back up to the top here. Again, I'm not going to show you everything, but so read one character. So we read 2 characters actually, because new line is a character. So if you want to read the number 5, you type 5 and hit return. So you have to read 2 bytes, not 1 byte. Everybody always forgets the new line character. Pick system call 3, which is read. Invoke the operating system. The operating system will get the interrupt handler will be like, oh, you're trying to do read system call. It jumps into the read system call. The read system call says, okay, I'm going to write into that memory address 2 bytes from standard input, and it does it for you. Boop, boop, and it returns. And then we load from the input buffer into register 1. Again, we have to do this because registers are not preserved through function calls, right? So a lot of bugs were caused by people just assuming that R1 would still have input in it. It doesn't. We load 1 byte from the input buffer, and so if I type in 5 and hit return, that will hold 5 with single quotes around it. 5 with single quotes around it. Okay. And so, did I change the greeting for the input tester? I don't know. Maybe that's why you guys didn't do well. So let's see, maybe I have to update the output file maker. Is there no input test for this? All right, so there you go. So try running the input tester, see how you guys are doing. Okay. All right, so let's see here. So if you read single quote 5, that's not the number 5. If the user types in 5 from the keyboard, that's not the number 5. You have to go to man ASCII. Man ASCII tells you where these things are. So ASCII 5 is decimal 53. So ASCII 5 is decimal 53. So what I do is I compare it against ASCII 0 and I compare it against ASCII 9. So in my code, I compare the value that the user typed in against ASCII 9. If the result is bigger, die. I compare it against ASCII 1. If it's smaller, die. Then I subtract ASCII 0 from it. So if they type in ASCII 5, which is 54, subtract out 49, I get the number 5. So that's how to actually convert from a digit to a number that equal to that digit in ASCII. So this would have R8 holding 5 in it at that point. I then preserve it into R5 for some reason. And then I'm going to do another load, another read, and I'm going to uppercaseify the things and stuff like that. So, like I said, I'll if the string was different, I'll give you guys till Thursday to do it. But you are getting your new homework assignment. You've already, in fact, gotten your new homework assignment. So let's start talking about that because I don't want to keep belaboring ASM bitwise over and over again. So become let's say cd into ASM hash. So for this assignment, you must make a hash table. You must make as fast a hash table as you can. All right? So right now it's going to run, pick a random seed, 10, 100 elements. It's pretty small. 10, a million elements. There we go. So pretty fast. So you can see that right now it takes 0.12 seconds to randomly generate a million ints. And then the no. Oh no, that's fine. That's fine. There was a bug where it was printing out the same timing information for these, but it's actually different on the third significant digit. Thank goodness. Did Kearney go over how the diamonds are made via the number in lecture? I did not. I did show you how the string works though. So what I did was I had a string just filled with dots. And what I would do is do repeated calls to write over and over again. Write, printing out 1 dot, write, printing out 3 dots, write, printing out 5 dots, and then going back down, write, printing out 3 dots, write, printing out 1 dot. You can do that with just one loop counter because the numbers aren't ever going to be bigger than 9. Or I guess, if you're doing the algebra, like whatever, it'll fit in a character, right? And so what you can do is you can actually bit pack the you can bit pack a single integer so that the lower 8 bits are I, when I counts from 0 to 9, and the next char over is the number of dots to write, and the next char over is the, I don't know, max or something that you're testing. It's I is less than whatever. And so what you can do is you can use left shift and bit masking to bit pack a single integer to hold all of your variables in just one int. It's pretty nifty stuff. And you don't have to do that, but it is cool. And oftentimes there's no performance penalty of it because you can do a right shift, right? So you can do a right shift. So let's say that the upper 8 bits aren't used, but like let's say you've got bits, the third byte over holds like your maximum, I is less than 10, so it'd have 10 in it. So you can compare I against this value right shifted 16 times. And so there's actually no performance penalty. To go the other way around, you would have to bit mask using bit clear, things like that. And store the result in another thing. Maybe, I think there's a way of doing it without that. It's like you left shift and right shift or something like that. But yeah, so basically the point is to have, to save on register space. If you have a bunch of chars, essentially unsigned chars, then you can bit pack them all into an integer. Kind of like Neon. It's literally what Neon does, except Neon does it for you kind of automatically. Whereas when you do this yourself, you have to right shift and bit clear and stuff like that. So yeah, it's really cool. One of my ARM programming books has like a whole chapter on those kinds of tricks where you can bit pack things into register to save on your registers. Because once you start running out of registers, then you've got to read and write to RAM, right? And RAM is slow. Hopefully your cache is going to pick up a lot of the burden on that. But even if you get an L1 cache hit, you're talking 4 cycles, right? Whereas a register is a no cycle penalty. Okay, so anyway, so for ASM hash, what it does right now is that it generates, in this case, 1 million integers, tells how long it takes, it then hashes them and searches them in C++, which takes 0.12 seconds to do a million, what would it be? 500,000, I think it does 500,000 inserts, and then, yeah, so it generates 1 million numbers, and then the first half it inserts into the hash table, and then the second half it searches for. So it's doing 1 million operations. 500,000 inserts, 500,000 searches. And then it saves the results into a vector. And then it calls your assembly code. And it saves the results of your assembly code into a vector. And obviously your code is quite fast right now because it is doing nothing, cat u.s. Your code right now is just printing, well, it's not doing anything, it just returns, right? So there's 2 functions you have to write, an insert function. The insert function takes all the input at once. It doesn't insert one thing. For efficiency reasons, I'm having it insert all the numbers at once. So that way you don't have a function call overhead, right? So basically you're given, I allocate the memory for you. I was thinking about having you allocate the memory, which would actually probably be a good learning experience for you. But basically all you do is you do a branch with link to malloc. Malloc takes a number of bytes and it returns a pointer. So there you go. So if you were to be allocating the stuff yourself, it would look like this, right? It'd be like move R0. I want to allocate 4,000 bytes. Branch with link to malloc, and then move into register, I don't know, 10 the results. And so this returns pointer to an array holding 4,000 bytes. So just think about having you guys do that, but then I was like, but that's going to put, because right now the time to allocate memory and clear memory is not counted as part of the time for the C++ code, and if I counted it as part of your time for assembly, then that would give you a performance, it's not an apples to apples comparison. So, yeah. But do you guys understand that? Like, do you guys understand how that works? Like, malloc returns a pointer into R0, and so I'm just going to save that pointer into R10 just so we have it around. What happened when the name got reset from Chibi back to localhost? It shouldn't. I literally checked the... damn, all right. There we go. Right. There we go. Machine has been successfully renamed. I don't know how that happened. Actually, I do know how that happened. The other server, the host name got reset, and so I think I mistakenly I had multiple buddy windows open at the same time. Okay. So hash. Okay. So what do you guys need to do? Let's take a look at the C++ code. You guys need to write these two functions here, right? So the first one, like I said, it's going to take a pointer to a big array that's been allocated for you already, and is going to take a pointer to a bunch of integers, and you're going to insert half of them. Okay, size is the size of your hash table, size is the size of the number of integers here, but you're only going to insert the first half, because the second half we're using to search. Okay, so insert the first size divided by 2. If you insert all of them, your running time is going to be terrible, because linear probing is terrible, okay, when it gets full. It's in general faster than chaining at low load levels. Okay. I don't know how malloc would work as assembly code. Did that make sense to you, Connor, when I just showed it right there? You just call branch with link to malloc, and it gives you an address, and then you can treat that address like an array, right? Like them move into register 0, 4,000 again. Branch with link to malloc. That will return a pointer. So I move into register 10, the pointer return, and then I could do things like say load a byte into register 5 from register 10, right? Or register 10 plus 100 or something, right? So register 10 is an array, and I can just read 1 byte at a time. Then I'll load an int at a time. I could do that, LDR. So that'll read 100 bytes past base, start of the array, 100 bytes past it. But if you had to do it without calling malloc, so your code doesn't have to call malloc. Your code should not call malloc, right? Or are you saying like if you don't have access to the standard library? Yeah, if you don't have access to the standard library, good question. So the system call that malloc calls is called break or sbreak. Both show up at the same time. And so basically sbreak, you just pass in a number of bytes you want, and then it returns a pointer. Boom. Okay, so this is very easy to use as long as you don't need to delete anything. The hard part about allocating memory is not the allocation per se, it's the deallocation. So malloc builds a data structure of all the different chunks of memory you've allocated. So like let's say you allocate 4K, you allocate 4K, and then you allocate 4K, and then you delete the middle 4K. Now you've got a hole there. So if you allocate 4K again, malloc will be like, okay, there's a hole, boom, perfect. But if you try allocating 5K, it won't fit in there, so you got to find another chunk of memory. And so over time, as you're mallocing and freeing, your memory gets very fragmented. But if you free two things that are contiguous to each other, then you have to merge them into And like if you deallocate 4K and 4K next to each other, now that's an 8K area that's open. You understand? And so the deletion is always the hardest part of data structures, right? And so malloc and free work on these data structures behind the scenes to allocate and deallocate memory. And they do things like try to keep things contiguous in memory so that you get better performance because of caching. Hey, you guys understand caching, right? And so if you allocate a linked list and you're allocating a node after node after node of a linked list, and you print the memory addresses, there's no guarantee they're going to be next to each other in memory, but a lot of times they will be. Because as you iterate through the linked list, malloc will try to put them all next to each other so that you'll get the caching. You load one thing, it grabs the next chunk of memory, go to the next pointer, oh, that's me, you know. And as you go along, you'll get a lot of cache hits. In fact, I saw a guy the other day who was benchmarking, and he was getting better performance from his linked list than he was with a vector, which is, I'm not going to say impossible, but like weird, right? Because if you're just like, let's say you have a linked list and a vector and you just want to print them all out, the vector should in all cases be faster, right? But he was getting better performance with the linked list than with the vector. And it was definitely a WTF moment, right? But you know, he investigated and he found that the compiler was actually optimizing the list away. It basically knew that what he was doing, and it just made the list vanish and things like that. But it didn't do that for the vector. So it was a very interesting experiment. It was an optimizer thing. It wasn't malloc even doing it. It was the optimizer figured out what he was doing and made his code vanish, basically. Anyone get issues in Bitwise where it doesn't print all the greeting? Yeah, you need to make sure you're printing enough bytes. Just increase the number of bytes you're printing. Should be fine. Make it 1,000. If you have a null terminated string, it'll be fine. Okay, so anyhow, yeah, if you want to allocate memory in assembly, call sbreak. Pass in 4K there, and it returns a pointer. Easy. As long as you don't have to delete anything, it's quite easy. So, sbreak increments the program's data space by increment bytes. With an increment of 0, can be used to find the current location of the end of the data segment. On a success, break returns 0. Sbreak returns the previous program break. So it returns the start of the array that you just allocated, essentially. And I believe you can pass in a negative number there. Yeah. Yeah, if break was increased, this is a value to the start of the newly allocated memory. But you can pass in a negative number there too. So if you pass in negative 4K, it'll deallocate it, right? And like I said, if you're allocating and deallocating willy-nilly, then you need to write your own malloc if you're not going to be using the standard library malloc. And that gets dicey. You won't have to do that in this class. If you go to Irvine, you'll have to do it, apparently. Okay. Anyone get into any of the UCs, by the way? I hear that the UCs are starting to send out acceptance letters. I'm getting to Berkeley, UCSD. According to the counselor I talked to today, it's only Irvine that's come out yet. The most distinguished of the UCs have not reached out yet. You mean UC San Diego then, right? My wife got into both Berkeley and San Diego and chose San Diego. Santa Cruz, cool, very cool. Congratulations. Just be aware at Santa Cruz, at least from the homework assignments my SPI network has sent back to me. Like they have you do data structures in C. Data structures in C. Probably a good learning experience. Kind of brutal though. San Jose State University yeah, I've had students go there. They say it's decent for computer science. I mean, you're right. The huge benefit of San Jose State is you're literally in Silicon Valley. Like Berkeley even is outside of Silicon Valley, right? It's quite a bit of a drive northeast around the San Francisco Bay. I mean, obviously the Bay Area companies hire from there a lot, and they offer a lot of money to Berkeley CS crowds. But if you're in Silicon Valley, man, you know, there's just, you know, you make connections like crazy. And I would highly recommend that. One of the most important things in life is just getting to know people and, you know, building relationships and things like that. So you need to be good technically, but you also need to be good socially. Okay, so let's talk about the code that I have right here. All right, so It starts off, I went over some of these learning points earlier. I showed you guys the random library. I modified it a little bit. I'll go over that in a second. I went over chrono. The kinds of things you guys have to write are these two functions here. So hash insert, again, we'll insert the first half of randos into hash table, and then asm search searches one value at a time. It doesn't take a array, and so it's going to have this function overhead, which I kind of, it'll probably slow you down. So if you guys want, you could probably, I'll allow you to refactor this. If you want to refactor it to do all of the searches at a time, but then you need to figure out a way of storing the results. Because the reason why I'm doing it this way is because it is going to call, it's going to call your search function over and over again and save the results into a vector. Okay, and then at the end, if the results from your code match the results from my code, it prints out your code's correct. Otherwise, it prints out your code's buggy. Okay, so if you can find out a way to refactor that, I will allow you to, because right now the C++ code does not have the function call overhead. So it's a bit of a, you're starting with a bit of a handicap, because there's a function call and you have to save the registers and restore the registers every time. So great. So let's go over this. So this is do you guys remember how I told you about how you could use like when you compile your code, you could be like G++, ++, -d debug. Do you guys remember that? And what that will do is that'll set a preprocessor constant, I guess, called debug to be true or something like that. And then you could write code like this. It's all like, you know, if def debug cout I end if. You guys remember me going over this before? This is very common in computer science, by the way. You gotta know this. And so when you compile your code, you can choose to turn on and turn off blocks of code. If def Linux, you know, you do the Linux system calls. If def Windows, you know, you do that. You remember? All right. So that is the C way of doing it. So this is how people do it in C world, right? The it's still done in C++ too. If you want it to be, if it really should be done as a compile flag, that's how you do it. But what I've done here is shown you guys the C++ way of doing it. Okay, and so I've created a variable here called debug. Looks very similar, right? If you set it to false, it turns off all of the debugging information. If you turn it to true, then it's going to start CRing, not cout, CR stuff, so it doesn't break the input tester. It'll CR a bunch of stuff, and you can see the hash tables and what values they have and stuff like that. Okay. Yeah. So you might be like, well, maybe we'll just use an if statement, right? Like if debug cout hi, right? You guys would expect something like that, right? You know what I'm talking about? What's the problem with writing our code this way, where, you know, we just make a regular variable, it's a constant variable, you know, you have an if statement and it checks to see if the thing is true or false. What's the downside of this? Bloat slows down the program. Yeah. Global's bad. It's not a global. I mean, I could have made it a global, I guess. Technically, it's a little bit less global than the compiler thing, because the compiler thing is going to probably turn that flag on for all your code, maybe, depending on how you have your makefile set up. Define Nick wrote this. If def Nick wrote this. Yeah, why are you even trying to call this code? What's wrong with this is that this is a branch, right? And so if you were to compile this code, right, the optimizer might turn this off. The optimizer might turn off, but let's say it doesn't. Then you're going to have a branch right here, right? And it's going to be slowing down your code. Whereas when you do a preprocessor macro, it actually inserts and removes code from your text file before the compiler even sees it. And so it won't generate any assembly ever. This code here might generate assembly. It might have a branch, you know? And depending on how good your branch predictor is, that might actually significantly slow down your code even if you never output anything, right? Because branches can be expensive. Are you guys with me on this? Okay, so let me show you the better way. If const expr. You guys did not know this was a C++ class, huh? So this is, when was if const expr added? That's 17 that added that. When did they add if const expr? I think it, yeah, 17. Yeah. So it's fairly recent, right? Like maybe when some of you guys started college, it didn't exist yet, right? Depending on how long you've been in college for, I guess. The first head of the ACM at our school was here for 5 years at a community college. It's like Van Wilder. Okay. So anyhow, so I'm sticking to the preprocessor because you don't use 17, will you? Apparently not. You got a warning here. Right? So what this does, if const expr. So that's an if statement. That's the new hotness. And so what that means is the compiler will do the if statement. Okay? The compiler will do it. This code will be run by the compiler, not by your program when it runs. The compiler runs the if statement. So what that means is that this debug business here has to be known at compile time. Not at runtime. You can't have the user input debug to be true or false. But if debug is a const, which it is up above, then the compiler will look at this and be like, it's true, and then it will put this code in. If it's false, then it cuts the code out, and it will not generate any assembly for it whatsoever, not even a branch. Not even a branch. And so if you have any if statements that can be known at compile time, you should make them if const expr. Okay? Does that make sense, Dolio? So, yeah, okay. The anytime you see the const expr keyword, and C++ has been moving more and more in recent years to have the compiler run code for you, right? So like you can make a const expression function, and that function will be run by the compiler. And so like you can compute the Fibonacci numbers in the compiler. So when you compile your code with a const expr function, recursive const expr function, you pass in some number, the compiler will actually run the function and say, okay, the answer of Fibonacci 3 is 2, right? The answer of Fibonacci 4 is 3. You know, and so if you have a call to Fibonacci 4, if it's a const expr function, the compiler will actually run the logic and be like, okay, the answer is 4, and then it hard codes 4 into the answer. Anything that's const expr will not generate assembly at runtime, right? Instead of Fibonacci 5, 1, 1, 2, 3, 5. Yeah, instead of Fibonacci 5, it will replace all of that and just put the number 5 there as a numeric literal. It'll just put a numeric literal 5. Boom. And yeah, you can, yeah, it's cool. It's amazing how much they've been offloading, because runtime is what matters. Compile time, yeah, we want compile time to be fast, but if you could spend a second now to save a second every time somebody runs a function, that's a huge benefit, right? Const expr Fibonacci, and so this is a pretty famous demo here. Okay. Const expr long Fibonacci, return if n is less than 1, return -1. Okay. Otherwise, if n is 1 or 2, we return 1. Otherwise, we recursively call this way. So this is an order 2 to the n algorithm, by the way. Every increased number of the Fibonacci is going to generate 2 calls to Fibonacci. So if you do Fibonacci of 8, it does 2 calls, and each one of those levels do 2 calls. It's a 2 to the n algorithm. So this is pretty bad. It's yeah. So you don't want to implement it this way, by the way. Don't implement the Fibonacci recursively like this. It is incredibly inefficient. But that's the general idea of what you're trying to do, right? And so if you you can write a const_per function, and then it will the compiler will run it. You know? Okay. So yeah, the compiler literally runs the code and saves the result, so that you don't have to at runtime. It's really cool, and that's been a big push in recent years from C++ because it's a great optimization, right? Like if you're always going to be outputting the Fibonacci of 100, there's no reason to recompute the Fibonacci of 100 every time. Have the compiler run it once, and then save the result and just print the result, right? If anything is knowable at compile time, you don't need to recompute it every time. So this is pretty neat stuff right there. So if const_per debug, you see these are all throughout the code. And so basically if you turn debug on, then the compiler, there won't be an if statement. There won't be an if statement there. Even if debug is true, it will not generate a branch. Okay? If debug is true, it will literally just copy and paste these two lines into your code. There will not be the overhead of a branch, even if debug is true. If const_pers don't generate code. It's really nice. They don't turn into code. It'll obviously put that code in, you know. But the if statements themselves, the if const_pers don't generate code. So it's even better than if statement. Yeah. This won't, you know. God bolt time. Let's find out. Let's find out if I am BSing you guys or not. All right. So God bolt, save me, God bolt. Jimmy, come home at once, girlfriend. I don't know what's going on here. Okay. Struct mama. I don't know what's happening here. Okay. Include IO stream using namespace spaces standard. All right. So bool debug is true. If debug cout hi, else cout bye. All right, so this is on x86. Let's switch to ARM, not ARM64, ARM7, ARM 32-bit. Add, subtract, store byte, branch if equal, right there. Okay. So there's your branch, right? And I think that's probably going to be branching on L4, which is loading from L7, which, yeah, these non-optimized codes are pretty bad, but yeah, basically it's got a branch there. Now, if we were to change this to a const_per, this has to be compile time determinable. Const. True. Branch with, yeah. Notice how the branch is gone. Okay. It has a branch with link to see out the thing, but it doesn't. There's no branch there anymore. Okay. So pretty cool stuff. Need const on debug. Yeah. Yep. Well, I didn't put it on the previous one, so it wouldn't optimize it away possibly. All right, so that is a little bit of C++ knowledge for you guys, and let's see what else. Random chrono, yeah, let's go for that a little bit more. So I changed this from the default engine to the Mersenne Twister 19937, which, come on, standard library people, come on. Can you imagine teaching this? Week 4 of Computer Science 1, week 4. Professor, I want to roll a die for 1 to 6. Okay. All right. There you go. Type in MT19937 space generator, open parentheses, C, close parentheses, semicolon, uniform, underscore, and underscore distribution, open caret bracket, and close angle bracket, space distribution, open parentheses, 1, comma, 6, close parentheses, semicolon, auto roll equals bind, open parentheses, distribution, comma, generator, close parentheses. Now you've got a function called roll that will generate a number from 1 to 6. Congratulations. Is there a point to doing this? Define debug, ifdef, debug, and endef. Yeah, that's the C. That's how C world people do that. So the C world people do ifdef, ifdef, end else if, that kind of stuff. Const expr is the C++ equivalent of that. Yeah, and that's why in first semester I teach the C way of generating random numbers, just because how do you generate a random number? Called rand. That's it. Modulus it by 6, add 1. That'll give you a number from 1 to 6. Congratulations. So seeding a random thing is pretty easy. So I just read in a seed, passed it to the generator. That seeds it. I believe you can there's actually a seed class, and you can combine different seeds together, like the current time and the temperature of your motherboard and atmospheric noise and things like that. So I believe the seed class, whatever it's called, seed something, you can actually pass in multiple seed values and it will combine them all together to form a new seed if you really want to have random numbers. In this case, we do not want to have random numbers. We don't want random numbers. Instead, what we want is to get predictable output so that you pass the test cases. Okay. Can you use const expr with extern C? Probably not. I don't know. It's a good question. Const expr. Maybe. No. Guess not. I don't know. Let's try it. Maybe. I don't know. Got a warning for unused, but other than that, okay. Okay. So this is how you seed a random number generator, and I picked the Mersenne Twister because it's generally considered to be a good performance, good quality random number generator, rather than leaving up to the default, whatever that is, which might actually be MT19937. Sounds like the serial number of a starship. NCC. Okay. Okay. And so the user is going to type in a random seed, so you get predictable. You can get predictable random numbers, and then they're going to type in a size. One of the benefits of using the read library, you can't do this in normal C++, which is one of the reasons why I like the read library that I made. You can actually read from input and save it into a constant. You can't do that normally. Okay. So that's a constant. Can't change. You normally cannot read into a constant using C++ because take a look at this. Const int size 2, let's call it. Cn into size 2. Right? Can't do that. Won't work. Consts can only be set when they're defined. And so there's no way of embedding a Cn into this thing here. But with the read library, you can. Right? So you can prompt and read and save it into a constant all in one line. Okay. So if they type in a size of 10, then we're going to randomly generate numbers from 1 to 40. Because if we're generating numbers from like 1 to a million, then the odds that we're actually going to get hit on the table is fairly small. But if we only use numbers from 1 to 10 in like a hash table of size 1 million, we're going to keep getting collisions over and over again. So the range of random numbers that is made is going to be equal to 4 times the size of the array. So we get some hits, we get some misses, we get some duplicates. You guys understand? You put the language name next to the backticks, yeah. Okay. So also, do you guys understand why this is a multiply by 4? If you left shift a number by 2, multiply by 4. Okay. Logical shift left by 2. That's exactly right. Exactly right. So, yeah. I could have written times 4. I could have written times 4, but I wanted you guys to, I don't know, I wanted to quiz you on that, I guess. It just looks cool, man. It just looks cool. All right, and then bind, again, this is part of the hashtag functional library down here. And this will actually create a function. It'll bind a parameter to a thing that takes that parameter and returns a function object. And a function object can be called just like any other function. I could, cout roll a bunch of times. You can see I get random numbers out of it. Pretty cool, huh? I think it's cool. This is garbage. from a pedagogical standpoint, from a teaching standpoint, it's absolute garbage. But yeah, the end result of it's pretty cool. You just call roll and it gives you a good set of random numbers, the range that you want. Frankly, though, the way Python does it is just better. They just have this by default. Give me a random number from 1 to 6. Done. Easy. Okay, so yeah, there's no difference from a speed perspective if you're doing a multiply or a left shift. If you have the optimizer turned off, there would be a speed benefit because left shifting has no cost, and multiplying by 4 is a 4-cycle cost. So up to a 4-cycle cost. So if you're running your code without the optimizer on, yes, this will be faster. If you're running with the optimizer on, the optimizer will absolutely convert a times 4 into a left shift, for sure. And if you're worried about the running speed, why don't you have the optimizer on? The default generated code is horrible. Horrible. Like if you have the optimizer turned off, it makes bad assembly. Because it leaves it up to the assembler to go through and eliminate all the redundancies and stuff like that. It just wants code that's correct. And it leaves it up to the optimizer to pull the worthless stuff out of it. Okay, so here we have a vector called randos of size 1,000,000 or whatever. Steady clock, if you remember, is part of the chrono library. So this gets the current time, the type, who cares? We're in Python world now. Yay. What's the type? I don't know. Okay. And then we generate a random array. So this is equivalent to writing for every integer in randos. So this code here is the same as this code here. Same thing. It's actually a little bit more concise to write it yourself. But like I said, it's in general a good idea to use the standard library because the standard library expresses your intent more. If you're just doing a for loop, the compiler has to guess what you're trying to do. And if you're using generate, then the compiler knows I am generating a random array, basically. I'm calling roll on every element of that random array. And if somebody were to come in later on and parallelize generate or add neon code for it or something like that, then your code would benefit from the neonification or the parallelization of generate. Whereas if you have a for loop, you got to use the OpenMP stuff. I showed you guys OpenMP last time, right? Did I show you? The parallel for loop. OpenMP. Did I show that to you guys last time, or was that 41? Do you guys remember? Did I? I don't know. I don't think so. Okay. Let me show you that then. I don't want to get too distracted, but OpenMP parallel for loop C++. It's the world's easiest way of generating parallelized code. You just put that in front of the for loop, and then it will parallelize. But he should be including the OpenMP header. Whatever. So basically, if your compiler supports OpenMP, OpenMP is like I said, it's the world's simplest way of parallelizing. If you got multiple CPUs or whatever, then you just toss that in front of a for loop, and then the for loop will be run on different CPUs. And it just leaves it up to the compiler to figure out how many CPUs it should run on, things like that. If you got a 20-core system, it might, in theory, just split it off over 20 CPUs. Can you use that with generate? Well, my point is that with generate, they're adding in C++20, they're adding policies, I think they're called, parallel policies. And so generate could be, you could pass essentially a flag to generate saying run this parallel. And then it will have a generate specific parallel implementation. OpenMP is not very good at generating good code. But if you have a situation like this where you've got an array and each part of the array has completely independent code from each other, like each element, like sometimes you'll make it so each element of the array depends on the previous element, then you can't parallelize it. But in this case, where we're just like each chunk of the array is independent of each other, then OpenMP will just sit there and split this across n processors. Okay, and you just compile your code like that, and there you go. It's now parallelized. Cool. So, yeah. So yeah, hashtag pragma OMP parallel, hashtag pragma OMP4. You got a for loop that's running 12 times, which is a strange thing, but okay, whatever. And then it is it's doing a parallel addition from one array into another array. Okay, so it splits off 3 different threads, and then when the for loop ends, they will wait for each other, then it will continue. And so it's a very, very simple way of doing parallel processing. It's not great, by the way. The speed of it is not great. I did show you the threads thing before, right? Where you just spawn off a thread, you can just do a function call, and thread, and you pass a function call, and that'll just run in a different thread. That's a very easy way of doing parallel processing too. This is, just try this out sometime. Just try that. You just compile your code with the that. So, how is using 8 cores only a 3-fold increase of performance? That's pretty normal, dude. If you're using 8 CPUs, you don't get 8 times the performance because there's an overhead to splitting it off into different cores and different CPUs. They don't share the same caches and things like that. There's an overhead to creating the different threads. There's an overhead for waiting for them to finish. And so you need to have a big enough problem size for it to be worthwhile, right? So, yeah. Serial version, OpenMP version. Okay, that's pretty good. So that goes from 25 seconds to 1 second, or 1.5 seconds, with 16 threads. So a lot better. Actually, better than 16 times. Super linear speed up due to caching benefits. Okay. You guys understand? It's a little detour. Just Google OpenMP. It can be as simple as one line, to parallelize your code. And trust me, I'm somebody who took multiple semesters of parallel computing, and it can be a real pain in the ass to handle it all manually and stuff like that. So OpenMP is a good starter gateway drug to the parallel world. So yeah, I took 2 quarters of parallel processing as an undergraduate, and then specialized in it in grad school, and took 2 or 3 quarters of it in grad school, graduate level parallel computing, and then I TA'd the class. Yeah, so I mean, I've done it a lot, and trust me, like OpenMP is by far and away the easiest way of doing parallel processing. Thread is pretty easy too. Fork and exec is also fairly easy as well. I would say start with the if you got a for loop. Unknown pragma. I don't have it installed. So, all right. What else do we have to talk about? The homework assignment. So, yeah. So generate. like I said, parallel policies are being added to C++ as we speak. And so if your library has a default policy of just using the parallel version of it, someday you might turn on your computer and the generate runs faster as it's parallelized. Until then, you might want to try, if you care about the generate time, you could try the OpenMP parallel 4. You can try spawning off different threads, things like that. Okay. So then we get the ending time. We use the duration class to get the difference in time from the end to the start, and we convert that to a number with .count. And so that is how you time code using the C++ way. In C world, you use things like time and clock. So time is a system call that is the number of seconds since the beginning of time. The beginning of time was January 1st, 1970. And yeah, so that is a second resolution, right? Every second it will update, which oftentimes isn't fast enough. So we use things like clock. It's part of the C library. So clock returns the number of milliseconds, or not milliseconds, microseconds. It's clocks per second, but clocks per second is always, yeah, it's always microseconds. So it returns the number of microseconds since your program began. And so very simple, much easier to use than the chrono library. Not as good quality though, potentially. So basically, clock just returns the number of microseconds since your program began, and you just subtract the two numbers and output it, and that's the number of microseconds your code took. As always, the C way of doing things is much more concise. Probably lower quality clocks, because steady clock and high resolution clock can actually have better resolution than the microsecond level. And then there's all sorts of like duration cast and things like that you can do with chrono to output the format in different formats and things like that, which you don't get with clock. Clock just gives you an int. It's been 100,000 microseconds. What cases is it lower quality? Well, what if your code runs in 2 microseconds? If you use clock, you might get 2, you might get 1, you might get 3. And so there's going to be this huge variability in the timings of your code if your code's really fast, right? Clock won't have enough resolution to give you a good answer. Whereas if you use steady clock or high resolution clock from chrono, if the system supports a higher resolution timer, then you can actually get more significant digits, so to speak. Okay. So clock is basically fixed at the microsecond resolution by the POSIX standard. That makes sense, Reed? I actually use clock a lot still. Just because getting an int and subtracting an int is like in C, like everything's an int. What's a file descriptor? An int. What's a pointer? An int. Everything's an int. It used to be if you didn't give a type on a function, it's just an int. Everything's an int. Yeah. Not everything. You got floats and chars, but yeah. And so it's just very easy to work with clock because you just get an int and you subtract the end time from the start time. That's the number of microseconds it's been. Call it a day. Whereas with chrono, like we saw last time, this is actually about as concise as chrono gets. Chrono is actually an incredibly verbose header file that results in you writing very, very long, like on Stack Overflow. I was looking at some other thing last night, and somebody's like, here's a one-line thing to, and it was like, yeah, it was one line, but it was like, it literally scrolled off the edge of my screen. One-liner to like output some duration or something like that. I'm like, I mean, yeah. It's a different world. C world and C++'s world are different. All right, so here we've got the results vector. So the C++ thing is going to be pushing the results into the results vector. Your code is going to be pushing the results in the results2 vector. If you wanted to refactor this to get rid of the function called overhead, then what you could do is every vector. Did you know that a vector is a wrapper around a pointer, basically? Do you guys know that? It's like a vector is just it's a C-style array with like a couple pointers to the beginning and the end and to the secret end. because oftentimes the end of the vector isn't actually the end of the block it's allocated. It'll have a beginning, it'll have an end, and then it'll have the secret end. And then once you hit the secret end, then it reallocates, it doubles in size, copies the elements over. But it's just basically a C array. So did you know that you could get the C-style array out of a vector? So if you wanted to pass a vector to an assembly function, you can do that. You can do that. Did you guys know that? So if you wanted to do that, then you could. The trouble is the vector itself wouldn't know about the pushback because you're writing directly into it. So you'd probably have to refactor the code to push back a lot of zeros into it instead of using reserve, like actually push back size zeros into it, and then you could pass the pointer to it and you could write values into that. Like if you wanted to do it that way, you could refactor it like this. So then the vector would start with 1,000,000 elements in it or whatever, and then when you pass the pointer to your assembly function could just write into it. If you want to do it that way, it would probably give you a nice speed increase to refactor it like that. I will allow you to refactor this code. I just wanted to make it as simple as possible to begin with. The array be private, is it? It is private, but there's a getter for it. You could actually get the internal C-style array inside of a vector. CPP reference vector data. So there is a member function called data, and what it returns is a int pointer. Like if you have a vector event, it returns an int pointer. What is that? That's the pointer to the internal array that it's got. Returns a pointer to the underlying array, serving as element storage. A pointer is such that it's always a valid range. Yep. So, and you can pass that to an assembly function and have your assembly function write into it. And as long as you're not doing anything else at the same time, that might trigger a reallocate from the vector, A-OK. A-OK. And this is deliberately here for that reason, so that you can call assembly functions or C-style functions with a vector. And as long as they're not calling pushback or, as long as you're just treating it literally as a C-style array, a fixed chunk of memory, they can read and write to it to their heart's content. So if you have a vector of integers here containing 1, 2, 3, 4, and you've got a function that takes a integer pointer, then you can just pass container.data, and that will grab a pointer to the internal array and pass it in. And you need to pass in the pointer and the size, right? Whenever you do anything with C-style arrays, you need to pass in a pointer and a size. It's always base plus offset. If you just have base, bad times, right? I was helping Nate Beal yesterday, and his code was passing in the starting pointer, but not the ending. So, and then you can just treat that like it's a C-style array. Or if you're in assembly, LDR, right out of that memory address. It's dangerous. It's only as dangerous as reading and writing to any array is. You just have to make sure that the vector. Good. I didn't save it. Good. Just make sure that the memory is allocated before you read and write into it. Right. Right now, yeah. So change it like how I just showed you. If you want to refactor that way, because this assignment will give you extra credit. You are going to be graded on the speed of your implementation. Okay, so yeah, your code has to be correct. Your code needs to print out your code is correct, and that's a C on the assignment. But then your grade past that point is how fast your hash table is. You cannot make your hash table bigger. You can make your hash table smaller if you want. Because obviously an easy way of increasing the speed of a hash table is to make it bigger. No, can't make your hash table bigger. You make it smaller though, if you want. So like if you want to make it a prime size, having a prime sized hash table is very common. Just, the memory's been allocated, but just pretend it's a smaller array. You want to make it a power of 2, go for it. Just find the next smallest power of 2. Are you making your own hash function? Yes. You're going to be hashing integers, so. Here's the hash function here. Okay. If you want, you can make a C function to do modulus and call it. I'm not gonna complain about that. Modulus is annoying to do in assembly. True story. You can write helper functions, but the core logic needs to be in assembly. Let's put it that way. My code, by the way, doesn't use modulus at all. So there's a, if you think about it, you might be able to figure out how I did it. I'm not going to tell you right now. All right, so yeah, so this is linear probing. You don't have to use linear probing. If you know other hash methods, quadratic, double hashing, feel free to use those. This is linear probing right here. So so yeah, the first half of the randos. This is the random numbers we made. The first half we insert. So we start off by, does anyone not know how Hashtable works? I guess we should probably talk about that first. Anyone not know Hashtable? No, that was good. All right. So basically, if we're going to insert the number 15 into a hash table of size 10, 15 modulus 10 is 5, so it's going to go into bucket 5, array element 5. And if that element is 0, by the way, 0 can't be inserted into the hash table. We're using magic numbers here, people. 0 means the bucket's open. So the random number generator generates numbers from 1 to 10 or whatever, right? It doesn't generate 0. So so while the address is not equal to 0, so while the bucket is full, move 1 to the right. And then when this while loop finishes, then it will write that random number into the bucket that is open. There cannot be an infinite loop here because we are only doing half the elements. So there will always be an open spot. There's no deletion. You guys do not need to do deletion. Deletion is always the most annoying and difficult part of every data structure. You do not have to do that. You have to do insert. You have to do search. This is insert. This is search. Okay, so you're translating literally a dozen or so lines of code into assembly. Okay. Yeah. I was helping Nate, like I said yesterday, and he's taking a senior level class, and they have to write a hash table with linear probing, and they don't have to do delete. I'm like, dude, my 41 students right now are doing the exact same assignment as you, and they have to do delete. And then his thing, it can, like, you don't have to bounds check, like you don't have to like worry about the array being full, like they do absolutely no error checking in that class. And I'm like, man, my second semester people are doing a harder assignment than that, It's ridiculous. So yeah, just insert and search. You don't have to do delete. They're seniors in college, It's like, come on. Delete is hard. It's not that hard. It adds complexity. It's not really that hard. It's not easy. It's not hard. It's kind of annoying to deal with. All right. So yeah, for searching again, so searching, we are using the second half of the rando library to search. So like I said, if we have a million numbers, the first half are inserted, the second half are searching. And so we start off by jumping to the bucket that it should be at. And if the spot is not open, then we check to see if it is a match. If it's a match, congratulations, we found it. It should break, actually, at that point. That's actually a huge... Ooh. Yeah, hang on. I'm not going to make it that easy on you guys. 1 second. Who wrote this code? Do not keep going once you found it, you know what I mean? All right. And then it puts the result in there. And if it ever finds an open spot and it has not found the person yet, then it puts false in there. So let's see what kind of difference in running time this will make. Random seed of 1, we will do 2 mil, 2,000, 2 million. So quarter second, rebuild. Quarter second, okay. I guess there's enough open spots in there that it's not a big performance penalty. But, yeah. Pseudo, has anyone written anything in that assignment yet? You finished it already? Okay. Do it again. It'll be good for you. All right. I think that you guys kind of have an idea of what should be done here. So yeah, so it will basically search over and over again, and it puts the results into the results array. The results array isn't going to reallocate because I've reserved enough room for it. Actually, twice as much room as I need, technically. So the results array won't trigger any reallocates on the pushback. So it's a little bit of an optimization right there, pre-allocating memory. Check the time. Okay, and then for your assembly code, notice this. Do you guys see that? Do you guys know why I did that? Have you guys ever seen an anonymous scope before? I think I talked about this earlier in this semester, right? Hazelton, have you ever seen an anonymous scope before? Yeah. So basically, I do this because in the first one up here, I make a variable called table, and then down here I make a different variable named table, and I wanted to just copy and paste my code mostly, you know, and so I just, by putting it within a scope like this, then I could have two completely different tables and just copy and paste the code without, you know, having to change the name of all this stuff, all these tables. All right, and so it is going to call your function, and you will insert the first half of randos into table, and then it's going to for loop, and it will search for this through the second half. So starting halfway through, going to the end, it's going to search over and over again. Save the results into results2, and then at the end of the day, compare the results. So basically, if you get your code is correct, that's 7 points, and then past that, your speed will be your grade, and I will sort. Once I kind of get a feel for how long you guys are taking on this, that will be. I don't have a table for how many points it's worth right now. I need to see kind of where you guys are at, so then I'll allocate the points accordingly. So as of right now, just try and make it as blazingly fast as you can. And there's a lot of cool approaches you can take to it. I don't want to give too many spoilers. I want you guys to think about it. But there's a lot of really cool approaches you can take to doing this very quickly. Okay. So that is your homework. You'll have a week to do it. Any questions? All right, so we didn't quite get through the lecture on call. Oh, I should mention the midterm you guys took last time. The midterm, you guys did pretty well on it overall. One of the questions had a mistake on it. So I threw that question out and just gave you guys the points anyway. So basically everybody got a free point on the midterm. And then I also rounded up. So somewhere between 1 point and 2 points, rounded to all of your grades. And then the coding section, most of you guys did pretty well on also. So well done overall on the midterm. If you guys have any questions about it, let me know. But I do want to finish this lecture on call. So call is the acronym for how you go about making a new program, right? You compile the code, which goes from C++ to assembly. You assemble the code, which goes from assembly to object files. You link it, which turns the object files into an a.out. And then loader goes from an a.out on disk to a running program in memory. And then we're going to talk about static versus dynamic linking today. So the linker not only takes your .o files, but it also links in the libraries as well. So there's a set of default libraries that get linked in every program. And let's see here. Pybim test.c. Oh gosh, it's already existing. Float sign of 5, whatever. GCC test.c. All right, I need to include CMath. Actually, it's not called CMath because we're in C world right now. It's just math.h. Compile it. Expected declaration of specifiers or ... Jeez. Float whatever equals sign. I have no idea what that was about. So let's run it. And so, do you guys notice that this worked? That worked fine. Where is that function? Because somewhere there is a .o file or a library. A library is just a collection of .o files. The library, have you ever seen a .a or a .so file? That means a library. So a library is just when you take a bunch of .o files, you put them together for convenience sake. We name that a .a file. So there is a program called R, which stands for archive. R. And basically you just archive a bunch of .o files together, and we call it a .a file. But did you ever wonder, where is that? It's not actually in math.h. Like the full, it's not a header only file. It might be. It might be. Let's take a look at this. Sometimes the full definition of a function will be in the header file, in which case that is a-okay. Using scan sine. Oof. Let's try cosine then. Tangent. It's less likely to trigger on things. Yeah, you see that? Nowhere within this header file is the function defined, right? Include next math.h. Include cmath. Okay. Sorry, wrong one. This is the C version. Okay. Yeah, so you notice how there's like no source code in here that's like doing anything. It's a bunch of hashtag defines and stuff like that. The reason for that is because the header file just says, hey, there's this function called sign. It takes a double, returns a double, whatever. So where is the actual object code for that function found? Does anyone know? Where is the object code for sign found? And why do you not need to know about it? How can I compile this? Sign is actually located in a .o file or a .a file or a .so file somewhere. Math.cc. Math.cc is a source code. I'm talking about the actual implementation of it, the compiled implementation. Because the linker is going to look around through all the .o files and .a files and .so files that it knows about and link them into an a.out. How is this thing linking? Math.h doesn't have the actual function definition for sign in it. It's actually in a .o or .a file somewhere. So where is it? And why do you not need to know about it until now? It used to be, in fact, this code would not compile. So when I was in your shoes, if I typed gcc test.c, this code, well, it would compile, it wouldn't link. It would say undefined reference, sign, not found. And in fact, this is actually the case in a lot of systems. You actually kind of need to know what I'm about to say. If you want sine and cosine and tangent and square root to be linkable, oftentimes you will need to do this. -L, that's an L, not a 1. Lowercase l. -L-m. And what that does is that links in the math library. So the math library is in a file called locate libm. The math library, libm. Eesh. Too many files with that name, dude. There we go. GNU ABI hard float libm.so. So it's a .so file. Okay, so that is where the actual function object code is. It's in a library called libm, and it's a shared object file. It's a dynamic library, which is what we're talking about today. And version 6. Okay, so let's see if there's a libm.a. I wonder if they have a static version of it. They do. Oh, interesting. Yeah, they do have a statically compiled version here. But yeah, look at that. Yeah, so you can either compile it statically or you can compile it dynamically, and I'll talk about what that means in a second. But basically, that right there, if we nm it, remember nm reads the symbol table. Anytime you have a .o file or a a.out or something like that, I can go nm a.out, type to less, and it gives you the list of all the functions that are in that program. Right, so the program I just made, test.c, it's got, these are the different segments, the data start, it tells you the offsets of them. So end and start are going to be in there somewhere. And then there's going to be a main in there somewhere. There's start, that's where it begins. And then it's got an undefined function called printf, but it found it in the libc, the C library. And so I'll explain how that works in a second too. Where is sign? Where is sign? Sign. You know what? I think it optimized it out. But whatever. Oh, dang it. Look at that. I typed exactly the same random characters. Oh, almost. Not quite. Okay. There. Scanf. Let's make this a double. So we will read from the keyboard a double. and then see the result in there, and printf. This is how you do cin and cout in C. Scanf, printf. Aha! Look at that. Yeah. So now that it didn't optimize it away, look, undefined reference to sign. Okay. So this is what the Catholic Church is always looking for: undefined references to sin. So if we wanted to compile this code, -lm, and it works. All right. So how does it know where math.h is actually in the first place? Does it have something to do with the angle brackets versus double quotes? Very good. Yes. In fact, that's exactly how it works. So when you install your compiler, you set up what the default include directories are. And so angle brackets mean they are part of the system installed header directories, and those are in two places. User include math.h, right? And then the C++ ones are in subdirectories there. But yeah, that's where it looks. If you put angle brackets, it looks in that directory. And then where is locate libm.a? That is in user lib. So user lib is the default place to look for libraries, which again, a library is just a collection of .o files. So do you guys understand what I mean by that? Like if you have a bunch of .c or .cc files, you can turn them into .o files. And I could distribute like 100 .o files to people, but it's a lot easier to just package them into one .a file. And then that has all the different object code in it. Does that make sense to you guys? So when I say this -lm, whenever you say use a library, the -l means use a library, right? And so it always prepends the word lib to it. So it's just an old clunky kind of thing. If you say -lm, then that looks for libm. If you search for I don't know, libc, like that. Okay. And that looks for a library named libc. This is libm. So the -l prepends the word lib to it, and then looks for either .a file or .so file.
Mailbox?
Yeah, and can you turn the light on behind me, girl?
Okay.
And close the door. Thank you.
Okay.
How do you link the .os into a .a file? Yeah, in curses, right? So if you were to link in curses, that would be locating lib in curses. .a. Yeah. So when you link in curses like that, it literally looks for a file named lib in curses .a or .so inside of user lib. Okay. And if you want to add additional directories to search through, there is -L user lib foo or whatever. So you can add additional library directories to search through. If you want to add additional header file directories to search through, -I user include whatever. Is it user include or is it wait math? Yeah, user include. Yeah. So you can use -I to add user include to or whatever. And so you can add additional directories to search through for libraries, for header files, things like that. And so if we were to nm a.out now, you will see somewhere within here it is going to call sign. Did I compile it correctly? gcc test.c drop sign. Yeah, there it is. And so this is using dynamic linking. And so it's got a call to sign. Sign is found inside of the glibc 2.4 library. Okay. So how do you link the .os into a .a file? Well, that is have the documentation on it here somewhere. You don't have to worry about it for this assignment. But basically, yeah, you can take .o files and use the AR command and turn them into a .a file. And so AR just takes the AR command takes the .o files, and there's a lot of options on it. I've got documentation on it somewhere. You don't have to worry about it for this assignment. Okay. So, yes. So, let's talk about this. So what happens is the compiler has certain libraries that it includes by default, and if the thing you're using doesn't, if you don't have the -lm, then it won't link it in. If you don't, like, this GCC is set up to not use libm by default, but I think G++ does. I think G++ actually will use it by default. G++, let's see. Yeah, so G++ will link in lib math, the math library by default. GCC doesn't. It's just how your compiler is configured. Okay. All right. So what the linker does, it goes through all your .o files, and we've talked about this before, right? If main calls function A, then it looks through all the different .o files, looks through all your libraries, trying to find a function named A. And if it can find it, then it copies it into the a.out. If it can't find it, then it prints a linker error. So, so you've been using libraries all along. They're kind of hidden behind the scenes. Printf, cout, these are all functions that are found in libraries. And yeah, there you go. Here's the command. AR, RCS, mylib.a, sepia.o, darken.o, bob.o, and then we'll take those three .o files together, smash them together, put them into an archive file called mylib.a. And so that's a library. And then you can just link against the library like you link against a .o file. There's literally no difference. You can use a .a file like it's a .o file. It's very, very simple. Okay. All right, so you guys are all talking about pizza. Does this make sense to you, though? Like, you can combine .o files together into a .a file, and then you can just link against it like that if you want. -L links against a system installed library, but you just, like, if you've got an archive file in your local directory, you just G++, main.cc, mylib, and then rather than having to list all these .o files, you just link against the library. I apologize, currently I'm hungry. I know, all I've had today is just a nutrition bar. How many calories is this? 180 calories. That's all I've had to eat today, plus whatever was in this half coffee I had. We were setting up a guided pathways for the school for computer science. So basically, when you start the school, it'll give you a sheet saying this is the classes we recommend and things like that. I'm fasting, and these dudes chatting it up about roundtable pizza. I'm right there with you, Shammy. All I've had to eat today is a nutrition bar. It's not quite fasting, I guess. Why don't C++ standard library includes have a file extension? You mean the .h? Because they did that to distinguish from the C ones. So there's actually a slight difference between CMath and math.h. And the difference is whether or not it includes the standard namespace. So everything in CMath is hidden within std::. Everything within math.h is in the global namespace. And so if you include CMath, then all that stuff is hidden within a namespace. If you hashtag include math.h, they're all in the global namespace. And so they changed it up that way just to distinguish between the two options. So it used to be like when I was in college, you included iostream.h. It wasn't iostream, iostream.h. You would include math.h. And it was with the more modern C++ versions, they created a separate set of the C-world functions, header files, that were all encapsulated within a namespace so that it doesn't pollute the global namespace. Hashtag include iostream. So where's it going to actually find the files? Yeah, it looks in the user include. So user include is where it looks for header files. And so I've installed bridges, for example, in the user include directory. And so you can just hashtag include bridges and have fun with that. Okay. So we need to talk about the loader a little bit. Then we can talk about static and dynamic linking, which is really important to understand, because some of the worst problems, not worst, but like annoying. Yeah. Some of the most annoying problems you're going to encounter in your career as a computer science major, assuming you stay as a computer science major. Sorry. In your career, like as a professional programmer, the most annoying things you're probably ever going to encounter are linker errors. Especially when you have a giant build and things aren't linking in properly, and you got to do a full recompile every time. Oh my gosh. Fully recompiling, like the compiler, like G++, takes like a day, you know. I think it's like 8 hours on my system to recompile it. And you forget one flag. Oh my gosh. Ugh. And on Windows, they have their own set of issues on linking and using DLLs and stuff like that. So anyway, so what happens? So when the user types a.out, what happens is we fork and we exec. And the exec is the loader. Okay, so the loader is almost a separate program, and it's a program that puts your program into memory and runs it. Okay, so you can do that with any library file. Yeah, you can put any library, any header file you want into user include, like cimage. Like I put cimage into the user include directory, and then you can just hashtag include cimage.h, and it'll find it because it's only root people with root permissions can do that. So users would use double quotes. For anything that's installed in your local directory, double quotes. Anything installed in the system, angle brackets, that's user include. And only root can put stuff in there. The number one programmer excuse for legitimately slacking off: my code's compiling. Hey, get back to work, compiling. Oh, carry on. Yeah, that literally happened to me. My coworkers were always like, why are you always in the break room? I'm like, my code's compiling, dude. It takes 3 hours to do a full recompile. And it's not working right, and so every time I edit the header file that everything includes, then everything needs to be recompiled, right? And it wasn't working, and they just always saw me in there like drinking coffee, reading the newspaper, because it was a 3-hour recompile, and it was super annoying, super annoying. Honestly, one of the biggest problems with C++ is the lack of a unified build system. You know, the industry is kind of seems to be coalescing around CMake and maybe Conan, probably CMake, to do this kind of stuff. But you know, Java actually has a pretty nice build system. Honestly, just every .class file turns into a .o file, essentially a .class. Every .java file turns into a .class file. And then when you include something, you literally provide the path name for the thing. So you don't have like a system installed directory necessarily. You just say include this /this /this, and it finds it and grabs the .class file and uses it. Java has a very standardized build system, and it works pretty well, honestly. Okay, so what happens when we run a program? If the shell forks, the shell execs the program, and exec sets up all the different memory segments. It reads the a.out, sets up all the different memory segments, passes in the command line parameters, clears the memory that needs to be cleared, branches to start, and goes. And that's it. And so technically you can run it manually, but I never do. Like, why would you do that? Just run the program, you know. And so the loader does one really important thing. And that is finding things in dynamic libraries. So what we saw over here is that sign is actually undefined. It actually did not link the sign function into the executable. The executable does not have a copy of sign inside of it. Instead, what it said was, we found it. It exists here. We found a function called sign inside of the standard library. And so what happens when the loader runs is that all of those things that are missing, get C and exit, all of those things that are missing but found somewhere else, that's when it finally grabs them and pulls them in. And so this is called dynamic linking. And the reason why we do this is so that we can update the standard library, and that will update all of our programs. So think about it. Let's say that you had a program like sine, a function called sine, does trigonometric sine function. And let's say there's a bug in it. Let's say the bug crashes your code if they pass in 0. If you were to statically link in sine, what that would do is it would find the object file where sine is and literally grab all of those assembly instructions and copy them into your executable. And then when you branch to sine, it just branches within your executable and runs the thing. And if you pass 0 to it, it crashes. Right? Do you guys understand how static linking works? That's called static linking. It's what you guys should be used to. It searches through all the .o files. I'm calling function A. Okay, here's function A. Here's all this assembly code. It copies it in. I'm calling function B. All right, here's function B. It copies it into your A.out. That's called static linking. It grabs the assembly from all these different .o files and .a files and sucks them all into your A.out. And it makes a really big executable. Dynamic linking, though, says no, don't copy it in. We found it. The linker is happy. We found it. It's somewhere in our system. It's within the GNU libc version 2.4 right there. But don't copy it into the A.out. So that has two benefits. One, your executable is going to be a heck of a lot smaller, right? Heck of a lot smaller. Will maybe be slower too because you've got to the loader's got to find these things when you launch it, but it's pretty fast. And if you wanted to, you can actually static link the standard library using the -static libs. Yeah, we just do that. We'll just use C++ for that. Static standard lib. I rarely do this. There, let's try that. GCC static standard lib. Test.c. Static lib go. Yeah, I don't do this very often. Static. Okay. Undefined reference is sine -lm. There we go. So if we nm A.out now, then look at all the stuff that got copied in. Look at all these things. There's not a single undefined function in here. You guys see that? Every single thing has been copied in. The entire standard library basically has been copied in to us. Okay. And if we see how big our executable is now, our executable is chonky. Our executable is 552K. Whereas if we did this with dynamic linking, it's 8K. So by statically linking in the standard library, it's literally copying all of those object files that we need into our A.out. And that's a massive bloat in size of the executable. It might actually be faster because you don't have to go through that step of at runtime finding them and pulling them in. But sometimes we do this just because dynamic linking is broken. For example, address sanitizer doesn't work on our system by default. fsanitize equals address. You run it, see? LD is the loader, right? And so because the dynamic, there's a problem with how the dynamic loader is set up right now. You can't run address sanitizer on the Raspberry Pi. So you can get around that by maybe, let's see if this works. You can't do static with it, yeah. But for other issues, you can sometimes get around loader issues by just statically linking everything. Because this was a problem I had on the main server. I would update the compiler. The compiler would be looking for a version of the standard library that we didn't have installed, because the compiler and the standard library update separately on different cadences. And so the only way around it was to statically link it. And then it would generate an executable that didn't search for specific versions of the standard library. And so, like I said, these issues are just super annoying to deal with. Yeah. So what is dynamic linking? So if I were to just compile this normally, it will, all of these things that are used are loaded, the loader loads them. So when I launch the program, it finds sign, right? It finds sign, and then it copies that. It doesn't copy it exactly, but you can think of it as then when you launch it, the loader will copy the assembly code over, okay? And use it. So you see how there's no offset, there's no memory address of this? It's because it doesn't exist until it's running. Okay. And the second benefit, the first benefit of dynamic linking is the size gets a lot smaller. The second benefit is, let's say there was a bug in sign, and sign was buggy, and sign would crash if you passed in 0 to it. Somehow happened, right? If you use dynamic linking, you can fix it. Because I could update the standard library. The standard library updates, the bug in sign is fixed. Now when my program launches, it pulls in the latest version and uses it. Hey, automatic bug updates, right? So my program only has to carry my code. All the standard library code will just get yoinked in when I run it. And so as the standard library gets faster, as the standard library gets more bug-free, then my program just upgrades on its own. It's really nice, except when it breaks. Except if they introduce a bug, right? Which can happen, right? Or if they introduce an incompatibility. Your code was linked against one version of the hash table, and then they change the hash table so it has a different memory layout, and you try calling the old thing and it crashes your code. That's called an ABI break. We've talked about ABI breaks before. And the only way around that is to just do a full recompile of your code. So dynamic linking and static linking have their own pros and cons. There's no right answer to it. Okay. So yeah, like if you're making a game, you don't want your code to have a complete copy of all of DirectX and direct sound and direct input. You know, it's a huge, your executable is absolutely gigantic. You have to copy all that stuff into one executable. Hell no. Instead, what you do is your code will just have that reference in there saying, I'm calling this rendering function over here in the DLL. And when you launch it, the OS finds all the DLLs your program needs and dynamically loads them together. And in fact, at runtime you can load a library at runtime. So you can actually do things like go through all the DLLs in your local directory and load them all. And now you've got access to new functions and things like that you didn't have before. It's cool stuff. Yeah, so you've got a variable called LD library path. It's kind of what I was referring to earlier. And so it's just the current directory right now. But if you compile your code with -L, you can add, public to it or whatever. And then it'll look in the public directory for libraries. This is a compile flag. If you want it to be permanent, you could add public to your LD library path. And then it would always look in that directory for libraries. Static linking copies the code in at compile time. Dynamic linking copies reference to code at compile time. That is correct. That is absolutely correct. So, yeah. So when you run the program, all of those holes you have in the program, all of these things here, the loader goes through and actually finally finds them and loads them into RAM with you. So these things are not in the executable. The executable, in fact, is very small. Right? So rather than 500K, it's 8K. All right, see you, Maria. Yeah. So there's pros and cons here. There's pros and cons. There's no one right answer. If you run into issues with dynamic linking, sometimes the answer is just to statically link it. I've had to do that in the past, like I said, like on the other server, I've had to. It's not something I do often enough. Like you saw that I had to like look up the flag, because it's not a problem that happens too often. It happens more often when you're using experimental builds and things like that. If you're doing the nightly builds and they update something and the standard library doesn't update, then everything breaks and you have to statically link until the standard library updates as well. So my general rule of thumb is this. I dynamically link by default, and then when that breaks, I use static linking, I guess. Kind of a good rule of thumb, I guess. But yeah, like if you need a specific version of a library code, and you know this shouldn't happen, but it does. Sometimes you need the older version of library code, then you can statically link that in, and you won't use the more updated code. So yeah, here we go. Oh, here are the flags, right? Static lib GCC, static lib standard C++. It is faster, probably, maybe technically, because you don't have to dynamically link stuff. Yeah, you're probably not going to notice it though. It's not a huge overhead. It does give you stability. If I was working in a mission critical application, I would probably statically link, because I don't want to take the risk of a shared object file, .so file. .so stands for shared object. It's a DLL in Windows, dynamic library. I do not want to take the risk that my system updates, the shared object updates, and it breaks my code. If I'm running something mission critical, I will statically link that bad boy, right? That is getting statically linked. I do not want the update cadence from Ubuntu to periodically break something that is keeping an life support machine running. You know what I mean? So, and yeah, like I said, when you get loader errors due to version incompatibilities and things like that, then your code just stops running. Like you have a working edit out, and it just stops working someday. And when you statically link, yeah, that won't happen, right? You've got the code that you need. It doesn't have to look around for your DLLs and things like that. So the downside of static linking is that your code gets a lot bigger, as we saw, and that can actually degrade your performance because of caching. It might actually be too big to fit into cache. I don't know. Might not. I don't know. Run it and find out. Okay. And then the big issue is that there are bugs in the standard library, and as you update them, your code will get the bug fixes without having to recompile. Okay. So, in general, I prefer dynamic linking, but occasionally it'll bite me in the ass, and I statically link it. Yeah. So. The downside also to dynamic linking is that you have to distribute your DLL, right? So if you statically link everything into one executable, all you have to do is give somebody the executable and they can run it. Whereas if you dynamically link and you put things into shared objects and DLLs yourself, you have to give them your executable and you have to give them all the DLLs. But now what happens if they have that DLL already, right? So now you've got your program and the DLL for DirectX with it, but they've already got the DLL for DirectX installed, and they have a newer version because your zip file is up on SourceForge, and it's been there for 10 years. And so all the DLL files you're including with your executable, because you have to distribute it with your executable, otherwise it won't work, all of them are out of date, and so you run it, and then you get what's called DLL hell. DLL hell is when like your code tries installing an old version of DLL, or there's, you've got 30 different copies of a DLL installed on your Windows machine, and the wrong one loads, and then your code explodes, right? And so it can be very annoying to distribute code with DLLs, because if you're giving somebody else's DLL, they might have a different version already. And do you overwrite theirs? Do you just use the latest version? Because your code was written 10 years ago. It doesn't know about the latest version. Maybe the latest version has an AVI break and your code breaks, right? So maybe you force it to use the old version, right? But now there's no benefit to using a DLL because you're not updating when the thing updates. So Yeah, and so there's no one really good answer to this. I think Java has a better answer to it. Java, if you compile something under Java, it'll basically run under any system. You know, Java has what's called a jar file, Java archive. It's like AR, but for Java, Java archive. And you can just jar up all your .o files, your .class files, jar them up and distribute it as one file, and run it. You run a jar file if you want to, and might waste some hard drive space, but things are cheap. Hard drives are cheap these days. Minecraft uses jar files. Do Minecraft mods come in jar files? Is that how they distribute them? Like I said, I only played Minecraft like briefly for during the first alpha. I was not impressed by a giant plain green field. Yeah, so that makes sense. So you just distribute a jar file and then people use it. It's just a collection of all the different programs they've compiled. There you go. So yeah, C++ had C++ was made a long time ago, and we're slowly getting to a point where we might be getting standardized abilities to download missing libraries, which is it's something that should have been made 20 years ago. But if you try running a thing and you're missing a .so file, it'd be really neat if you could just download it, and then I wouldn't have to distribute it with my code. So mod, server files, the game, everything's a jar file. Yeah, makes sense. So in that sense, I really do think Java has an advantage over C++ there. So a .so file is a shared object file, and you make it like this. So gcc-shared outputting to libreadint.so, readint.c. And so that turns a .c file into a .so file, and you can have multiple .c files, and it'll bundle them all up and put them into a library, a .so library instead of a .a library, and that's it. So and then you can distribute that to people, and if they want to link it, they use -l readint, like that. And oftentimes the library is actually after the source code. And so that's it. That's our lecture for today. So you will be given an assignment where you will have to make an archive and share archives between your partners and you, stuff like that. It's kind of a fun assignment. But for now, just work on the hash table thing. Get that done. Speed it, make it speedy as possible. We care about speed in this class. So, all right, it'll be fun. All right, see you guys.